Hi there, welcome back to the Formulaic approach. Now in this video, we are going to be doing justice to the topic of gravitation. So we'll deal with most of the things you're going to see in your exam. I'm going to explain with calculations. I'm going to derive formulas, solve calculations with you. We're going through all the nitty-gritty of what you need to know at least before you go into your exam. As far as gravitation is concerned, gravitational force, as you may find it in your textbook. But in the meantime, I'd like you to see this textbook that I've been talking about. Make sure to get yours, okay? I've got mine. Now, that is for those of you that have problem with mathematics, because we are going to be dealing with a lot of mathematics in this topic. So you cannot afford not to know maths if you are doing physics, okay? So this topic, this textbook is a teach yourself math textbook, okay? It has international and both national exam questions answered there. So if you are preparing for international exams, in fact, you'll see your past questions there. So it's voluminous yet affordable. Okay, so that's it for that. Let's go on to our topic. So what is gravitation? So we're going to start with what we have learned before, the four fundamental forces, right? So there are four fundamental forces. We said there are four fundamental forces. And it happens to be that Newton's gravitational force happened to be one of the fundamental forces. The first fundamental force is what I would call the gravitational force that we want to address. Gravitational force. So, but of course, we have the electrostatic force. So, electrostatic force. Then we also have the weak nuclear force and the strong nuclear force. So, but primarily today we'll be talking about the gravitational force. Now, as far back as the 17th century, a certain smart man, Sir Isaac Newton, who is arguably by far one of the greatest scientists, Sir Isaac Newton was the one that discovered that there was a force of attraction between bodies in the universe. Okay, so he discovered this in 1665, but I think he published this idea rather in 1687. Okay, so but my point is that what was his observation? His observation was that let me first break it down. Okay, so there is matter is the universe is comprised of matter, right? So matter makes up the universe. So, and of course, matter exists in time and space. The universe is basically time and space, right? So the space is for occupancy, right, by the mass. So mass is a fundamental property of all matter. Is that clear? So it means that there will be no matter without mass, because matter has to exist as something. That's how we define mass. We define mass as the quantity. Mass is the quantity of substance in matter. Quantity of substance in matter. The quantity of what makes up matter. The quantity of substance in matter. So it basically means that matter is mass. Okay? Even though we also know that charges are fundamental to mass, but to matter, it is fundamental for you to also know that mass, we would say that mass is more fundamental to matter than charge, because matter can exist without a charge, but matter cannot exist without mass, because mass is what makes up matter. I hope you understand what I'm trying to say. Okay, so he now observed that there was a force of attraction between masses, between objects in the universe, okay? Between objects in the universe. He was trying to draw the picture of how the universe is, okay? How the universe works. So, and he made a postulation which states that every object in the universe, his postulation goes thus, that every object in the universe attracts. Now keep in mind that Newton's force is attractive, always attractive, not repulsive. So that's what differentiates it from electrostatic force. Electrostatic force can either be attractive or repulsive, but Newton's force is always attractive. So every object in the universe attracts every other object with a force which is with a force that is directly proportional to the product of their masses, but inversely proportional to the distance, to the square of the distance r between them. All right. So mathematically speaking, what this law states is that the force of attraction, keep in mind, always attraction, between two masses, M1 and M2, is direct proportional to the product of M1 and M2, okay? But that force is inversely proportional to the square of the distance r between them. In your textbook, level, you might see d is the same. So but I like to use r, so we're using r because we'll be dealing with the radius of the universe and all that thing. So the distances we're talking about will be based on r, okay? So, and this is the basis of celestial mechanics. Let me put that down. This is the basis of celestial mechanics, okay? Celestial mechanics. Now listen. So if we put this together in mathematics, this becomes what? F is directly proportional to M1, M2 over R squared. By the time this changes to equality sign, we'll put a constant, right? F equal to K M1, M2 over R squared. So Newton was able to also estimate the value of this K, and he called it G, okay? So it's called Newton's gravitational constant. And the value is 6.67 times 10 to the power minus 11 Newton meters squared per kilogram squared. Okay? So how did I get this unit? Just do this by this, divided by M1 over M1 times M2. So that's how I was able to get the unit there. So G is that, so our force, gravitational force, Newton's force or Newton's gravitational force is given by G M1 M2 over R squared. Now, of course, another comparison I want to make is, if you remember when we were doing electrostatic force, we said that the constant K is 9 times 10 to the power 9, right? Electrostatic constant. The electrostatic constant. Or Coulomb's constant, that's what we call it. Coulomb's constant. Coulomb's constant is K, right? And the value is 9 times 10 to the power 9. But compare it to this gravitational constant. This one is several orders of magnitude less than it. Is that okay? So that's why you see, you necessarily don't feel the force of that. You don't feel this gravitational force of attraction as with objects as you will see in electricity. Okay, with electricity, we can already see attraction and repulsion of charges everywhere. Do you understand? With things that we, with our daily experiences. Do you understand? So, but on the celestial, so this force actually is only significant on the celestial basis. That is the basis of very large masses as great as the mass of the Earth. Do you understand? That's when you begin to see it. Because if I were to tell you now that, as you're watching me now, there is a force of attraction between you and I, you might not believe. You say, what is it saying? Okay, why am I not moving towards you? Okay, the reason is because this value of G already tells you how very small in magnitude this will be. So the masses have to be really great before they can really feel the attraction, this kind of attraction. Then of course, the inverse square is also an inverse squared law. It's an inverse square law. Now this tells you that the force against R, as the R increases, the force falls rapidly down. Do you understand? So as the R increases, the force really reduces a lot. As R is increasing, force reduces a lot. So that's why if the force, keep in mind, just follow me. If the distance, for example, increases by only a factor of 2, for example, you will notice that the force will reduce by, how do I need to reduce? If you know maths, the reason why I told you to buy that textbook, you know that when there is inverse relationship, as force is increasing, the distance is reducing. And as distance is increasing, the force is reducing. They are inversely related. But as masses are increasing, because they are directly proportional, the force will also be increasing. So force reduced by a factor of 4. If you work the math, that's the way it is. So if distance now increase by a factor of 4, force will reduce by a factor of what? By a factor of 16. If distance increases by a factor of 8, force will reduce by a factor of what? 64. Is that right? So the force also always reduced by a factor of the square of the distance by which the factor of the distance that it increases. Is that clear? Right. I hope you've gotten that concept. Now let's should we solve a question? Let's solve a question on this. Let me write a question on the board. And let's solve a question using that formula. Alright, now look at this question. It says that a spacecraft travels from the Earth towards the moon. The spacecraft travels from the Earth to the moon. And the mass of the Earth and the moon are this. So let's write our parameters. We have the mass of the Earth. Let's call that M sub E is 6.0 times 10 raised to the power 24 kilograms. And keep in mind that we'll be dealing with very large numbers now because they are celestial bodies, okay? So, and the moon, M sub M, is equal to 7.4 times 10 raised to the power 22. So, of course, you can see that the Earth is heavier than the moon, respectively. So, if the distance between the center of the Earth, and the center of the moon, the center of the Earth and the center of the moon, and just pardon me, I have to go here, of the moon is this. So let's draw the Earth. So let's draw the moon, which is slightly smaller. So this guy, the center of the Earth to the center of the moon, the distance between them, from here to here, okay? The distance between them is 3.76 times 10 to the power 8 meters. Okay, calculate its distance from the Earth. Okay, calculate the distance of the spacecraft from the Earth, where the spacecraft will be under zero gravity. So at which point will this spacecraft, let's call this guy spacecraft here, at which point will it be under zero gravity? It is the point where the gravitational pull of this Earth, the force of attraction of this Earth will be the force of attraction between the spacecraft and this Earth, and the force of attraction between, let's call this Earth first, let me name it. So there is moon and there is Earth. So there is force of attraction according to this Newton law between the Earth and this spacecraft. And there's force of attraction between the moon and the spacecraft. So where will this spacecraft feel zero gravity? It is the distance away from the Earth, where this spacecraft begins to feel the force of attraction of both of them cancel out. Is that okay? So that's the point where this guy will begin to feel zero gravity. The point where this force, the force of attraction due to this guy, due to this Earth, cancels out the force of attraction due to this guy. If we call the force of attraction from the Earth F sub E and force of attraction of the Moon F sub M, this point where the spacecraft will be feeling no gravity will be the point where F sub E will be equal to F sub M. So they will cancel each other out, because if you subtract, if you bring this guy to this side, F sub E minus F sub M will become 0. So that's the point where this guy will feel no gravity. I hope that makes sense. So let's call that distance from here to here. Let's call it a distance x, because we have to find that distance, right? Okay. Calculate its distance from the Earth. So let's call it x. That's what we're looking for. Okay. But we are already given the total distance. So from here, again, from that spacecraft, let's call this one ms for spacecraft, mass of. So that distance from here will also be, and let's call that one y. Okay, since this total is given, y will be equal to this one minus this. If this entire place is this, let's say this thing is 10, for example, and I'm looking for this place. If I call this place x, and the entire thing is 10, then this place must be 10 minus this, right? For this time, this number is given, so this place will be 3.76 times 10 to the power minus, times 10 to the power 8 minus x. Exactly, that will be the distance from the Moon. So now, but what is Fe? F sub E is the force of attraction due to the Earth, right? So I'd like to bring this here. Let me bring it here. So F sub E will be equal to the mass of the Earth, the Newton's gravitation times the mass of the Earth times the mass of the spacecraft, which is very small, over r squared. Now, what will this distance be? It is this distance x that we're looking for, right? So let me call it x squared here. Is that clear? So if that's the case, how about the Fm, the force of attraction due to the Moon? Fm will be equal to what? Mass of the Moon times the mass, Newton's gravitational constant times mass of the Moon times mass of the Earth, right? Mass of the spacecraft, rather. Okay, force of attraction between spacecraft and Moon. Over the distance again. Now this distance will be this, right? That will be 3.76 times 10 to the power 8 minus x all squared. So, but we said that thing will occur at where this is equal to this, right? So let's equate them. So that becomes g MEMS over x squared is equal to g m sub s over 3.76 times 10 to the power 8 minus x all squared. So g can take care of g here. What other thing can take care of? M sub s can also take care of M sub s. Is that clear? So what we're left with now is mass of Earth, which is given, right? So we have mass of Earth. So we are looking for x. Okay, so let's bring x's together. How can we do that? We have to open this bracket, right? We have to open the bracket. Okay, let's do this first. Let's do this. Let's write out what we have. M sub e over x squared is equal to m sub m over. Now, let's call everything here. Let's call it y. So let's call it y squared. Okay? Remember that y is 3.76 times 10 to the power minus 10 to the power 8 minus x. This is y. Okay? The reason why I'm doing that, I want to do something here. Look at what I want to do. So that this one will come here, they will interchange when you cross multiply, that kind of thing. This one interchanges, and we have y squared over x squared is equal to m sub m over m sub e. Exactly now. So I'll now have y over x all squared is equal to m sub m over m sub e. So that I can take square root of both sides, and square will cancel square root. So I now have y over x is equal to the square root of m sub m over m sub e. Is that clear? So from here, I can now conclude my solving by saying y is this, right? Y is this. So that's 3.76 times 10 to the power 8 minus x over x is equal to the square root of m sub m, that is mass of Moon, 7.4 times 10 to the power 22 over mass of Earth, 6.0 times 10 to the power 24. Okay? So let's take square root. Let's take square root of that side. Oh no, let's first divide. 7. This becomes 3.76 times 10 to the power 8 minus x over x is equal to 7.4 divided by 6 is equal to square root of 1.23 times 10 raised to power 22 minus 24. Exactly. So that becomes the square root of this. So 3.76 times 10 raised to the power 8 minus x over x is equal to the square root of this. Square root of, so you know this thing can become square root of 1.23 times the square root of 10 raised to the power 22 minus 24. And you know that this becomes the square root of 1.23 times 10 raised to the power 22 minus this is minus 2, right? So square root means 1 over 2. If you don't understand that, buy that textbook, okay? So cut this out, and then you have square root of 1.23 times 10 to the power minus 1. So square root of 1.23 will now give us 1.11 times 10 raised to the power minus 1. Exactly now. So over 1, we cross multiply again. By the time we cross multiply, we'll have 1.11 times 10 raised to the power minus 1, okay, times x is equal to 3.76 times 10 raised to the power 8 minus x. So bring this guy here, becomes x, right? Becomes plus x. So let's rewrite this. Times 10 raised to the power minus 1 means 0.111. Is that okay? So I hope you understand what I did. This is like just saying divided by 1 over 10. So if you divide by 1 over 10 to be 0.11, x plus x is equal to 3.76 times 10 to the power 8. So by the time you add it, it becomes 1x plus this becomes 1.111x. Is that clear? 1 plus this becomes this. Is equal to 3.76 times 10 to the power 8. Divide both sides by 1.11 over 1.11. And x will give you 3.76 divided by 1.11 is equal to 3.38 times 10 raised to power, that's 3.38. That's 3.4. 3.4 times 10 raised to power 8. Okay, it never really changed. It's just a little bit of difference, okay? Just a little bit of difference. So it means that we're very, very close to the moon. Is that okay? It is very, very close to the moon. So that is how to solve a question like this. It's all what I just did. There are simpler questions in O level, okay? So we are going to move to superposition. Let me clean the board. So as we also seen in this guy, electrostatic force, we can also superpose because they are forces. So we can see superposition of gravitational force. And what does the principle of superposition say? The principle of superposition says that the sum of forces, okay, the F net on a particular force, okay, the F net on a particular mass is due to the sum of forces, is due to the individual sum of forces. Let me restate that. The net force on a given object, on a given mass, okay, is going to be the sum of all the individual forces, okay? So in this case, we are saying the force of attraction, the net force of attraction on a body is equal to the sum of all the forces of attraction on that body due to all other masses. Is that clear? See, this is what I'm saying contextually. I'm saying that the sum of forces on one due to all other forces, let's call all the other forces net forces, is going to be equal to the sum of force on 1 due to 2 plus that on 1, comma, due to 3 plus that the force on 1 due to 4 plus the force on 1 due to 5 up to any amount. Do you understand? Force of 1 due to n. Is that clear? So I basically say that F1 net will be equal to what? The summation of all the forces. The summation of all the forces from n equals 1 to n equals to I. That is from 1 to I. Force on 1, let's use K please. K. The force from n equal to 1. You take the sum from n equal to 1 to n equal to k. So that is the force, all the forces on 1 due to k number of forces. Is that okay? Right. So that's what the principle of superposition is saying. Let me write the question on superposition. You see how to attempt it. So this question says that 3 spheres of masses m1, m2 m1 is 5 kg, m2 is 10 kg, m3 is 10 kg, respectively are located at the vertices of a 45-degree right triangle like this. So this angle is 45 granite. And it says to calculate the magnitude and direction. So there are 2 questions here. Of the total gravitational force expended on the small sphere. So this is the small sphere here. By the larger ones. Okay, so we want to calculate the force on this guy. So let's call this guy our sphere. Let's call it F1. Let's call this guy F2. Let's call this guy F3. I'm sorry, the force due to this guy F3, the force due to this guy F2, the force due to this guy here is F1. So what we want to calculate first is the force on 1 due to, let's first calculate for sphere 2. So the force on 1 due to 2 will be equal to G times M1, M2 over, so this will be M3, call this M1 mass 1, call this one mass 2. Okay, that's the way it's even named. Okay, that's the way it's named. So over R squared. So the distance between them, you have to take note of that. The distance between F1 and F2 is 2 meters, right? So we have F equal to G, which is 6.67, times 10 to the power minus 11, times M1, which is this mass 1, and M1 is 5 kg, times the M2, which is 10 kg, over R squared. What's the distance between them? 2. So that will be 2 squared. Is that clear? So from this, what do you have? You are going to have, you need a calculator. So that will be 6.67 times 50 is equal to 333.5 times 10 to the power minus 11 over 4 divided by 4. So equal to 83.375 times 10 to the power minus 11. So here, we'll bring this guy here so that it becomes 8.34 times 10 to the power, I've approximated, okay? 8.34 times 10 to the power. Now, minus 11 plus 1, because I moved here, so that will be minus 10. So that will be the F1, F2 on 1. Is that clear? Now, how about the force due to 3 on 1? The force on 1 due to 3. That will be equal to the same way GM1 now, but M3 over R squared. So now what's the difference between M1 and M3? Now this distance is not given. So you have to do something. Use hypotenuse squared is equal to opposite squared plus adjacent squared, right? This hypotenuse squared will be equal to what? Opposite, that is 2 squared plus adjacent squared, that's another 2 squared. So we can, you know, the hypotenuse squared is R squared here, right? The distance squared. So whether I solve it directly or I just use this directly is the same. Look at it here. Our R squared, the R we are looking for is already squared here. The distance we are looking for, which is H, is already squared. So we'll just pick this value and come and use it as 6.67 times 10 to the power minus 11. Then times 5 M1, M3, also 10. Okay, I think the question is even simple. So R squared is now 2 squared plus 2 squared. So that will be 2 squared plus 2 squared. So this top gave us 83, sorry, no, the top gave us 3.333.5 times 10 to the power minus 11 over 2 squared, 4, plus 2 squared, 4, that's 8, divided by 8. So that's just 333.5 divided by 8 is equal to 41. Is equal to 41.6, that's just half of this, right? 41.68, that's 69, approximately this, times 10 to the power 11 minus 11. So by the time we solve this, this will become 4.169 times 10 to the power minus 10 by conversion. Okay, I converted it to standard form. Now, how do we now find the actual force on that guy? So we have to take the sum of forces in vector sum of forces. So to take the vector sum of forces, this force F3 is actually has two directions. It has both x and y directions. It has x direction and y direction. X direction, we can resolve it to x component and y component. So what will be the x component? The x component of F3. So F3x component will be what? Let's call it F3x. F3x component will be what? The force, this F3, this force, to resolve it to x, that's we are closing. Let's resolve it to x. That means that we are closing this angle, right? So it will be F3x. What is F3? That's this guy here, Newton. Put Newton, please. The force is put Newton, okay. So that will be 4.169. So that's like 17. Let's use 2dp, please. Times 10 to the power minus 10 cos, we are closing 45 degrees. Okay? That will be on x-axis. Then which other force is on x-axis? This force is also on x-axis, right? So let's first deal with the y component of this guy. Okay, we already know the x component. F3x will be equal to that, cos 45. So 41 point that cos 45. That will be cos 45 times 4.17 is equal to 2.9 times 10 to the power minus 11. So that is like 95. 2.95 times 10 to the power minus 10. Sorry, minus 10. Okay. So if that's the case, so this is x component of this force. So let's do the summation of forces on x component. To know the summation of forces, we'll add the summation of forces on x component to know the F net, right? We add the summation of forces on x component plus the summation of forces on y component. So now this is x component. This guy is on x component. This guy is also on x component, F2 on 1. Or the F force of 2 due to force on 1 due to 2 is also on x component. It's only this one that has both y and x component. So we are saying that the summation of forces on x components now, okay, I've done this before in vectors. It's very simple. We'll add all the forces on x components. We have gotten the force due to this guy and force due to this guy. So this one is x component, right? What's the answer for this one that we got? 8.34. That will be 8.34 times 10 to the power minus 10 Newton plus, which other one is on x component? Now, this one will take the x component of this guy. So by bringing it down, we'll bring it down, it becomes 2.9, we got 2.95 times 10 to the power minus 10. So given that they have the same distance, we can factor that out. 10 to the power minus 10 is common between 8.34 and 2.95. So by the time you add that, 8.34 plus 2.95, that gives you 11.29. So our answer becomes 11.29 times 10 to the power minus 10. Okay? Let's leave it this way for now. How about the sum of forces on y component? The sum of forces on y component will be, this F2 is not on y component at all. The only force on y component will be this guy that wants to resolve to y component. You will resolve this guy to y component. You'll be opening this angle, and when you open an angle, that's sine, right? So it will be F3 sine theta, sine 45 degrees, okay? Now what is that F3? 4.17 times 10 to the power minus 10 times sine 45. Fortunately for us, sine and cos 45 are the same, right? So that gives us that 4.1, that gives us the same answer, 2.95 times 10 to the power minus 10. Okay? So if that's the case, then our summation resultant force, okay, resultant will be equal to summation of fx component all squared, resultant force will be the square root, remember that law, okay, in resultant forces, summation of f sub x all squared plus summation of f sub y all squared. Now listen, if you don't understand this thing I just did, this is for A level, okay? So what you will do is skip the video to the other aspect that, you see, there are some things that will explain this thing that are for answering, that will be useful for your answering of objective questions, okay? Because I've resolved things like this before. So if you don't understand it, I'll link the vector video in the description so you can go and watch that. But in the meantime, don't get bored. Skip to the other aspect. Exactly. So the resultant force would therefore be, let's call it RF, will be equal to summation of forces on x component give us this guy, 11.29 times 10 to the power minus 10 all squared plus this guy on y component, this is the only guy on y component, Newton. Okay, let's put Newton. So that will be 2.95 times 10 to the power minus 10 all squared. So what we simply do is square this guy. We will square 11.29 squared is equal to 127.46 now plus, now look at what I'm doing. Okay, more like times 10 to the power minus 20 right here, then plus 2.9 squared, 2.995 squared is equal to 8.7 times 10 to the power minus 20. So you see that times 10 to the power minus 20 is common, right? So let's just take the square root of, now this, if you understand what I want to do here, just stick with me. I will add this guy, 127.46 plus 8.7. In maths, I can separate this out and give me this times 10 to the power minus 20 times half. Okay? So it will give me 10 to the power times 10 to the power minus 10 back. So I'll now add this guy, 127.46 plus 8.7 is equal to square root of 136.16 times 10 to the power minus 10. So the square root of this gives us 11.6687. So that is approximately 67 times 10 to the power minus 10. So this will be the resultant force that will be felt by our 5 kg mass. All right. Now let's quickly move to the next thing. We have done superposition. Now let's deal with relationship between G and G. Relationship. So this is where you have to now listen. Relationship between G, the big G, and the small g. Okay? Let's establish a relation between the big G and the small g. So for a mass that is on the surface of the Earth. Now keep in mind that this force of attraction is evident in, if I throw this body down, you see it's coming down back, right? This body is being attracted back towards the center of the Earth. Okay? It's being attracted back towards the center of the Earth. And the center of the Earth here is downwards. The direction of center of the Earth is what? Downward. Don't forget that. In this Earth, in the Earth surface, within the Earth, the center of Earth, the direction of center of Earth, that will mean that every object is attracted to is downwards. So every object is attracted towards the center of the Earth. So we are saying here that if that's the case, then the force of attraction between them will be the weight of this body that is being attracted, right? And of course, this object has a mass, right? So times this, which is mg. So this is the weight of the object. But the force of attraction according to Newton is g, mass of the earth, times the mass of that body over the distance between them. So if we equate the forces, so we have that GMEM over r squared is equal to mg. Is that okay? Keep in mind that this r now, this r is going to be the radius of the earth, okay? Good, the radius of the earth, so I'll call it big R, okay? Big R. So in some places I might put r's of v. Let's put r's of v so that you know the radius of the earth. Now it has a value, it's a constant. So we'll have our formula becomes GMEM over big RE squared equal to mg. So m can cancel m, isn't it? So we can therefore have that g is equal to capital G m sub e over r sub e squared. This is the first equation between them, the first relationship between them. Okay, we have not been numbering our equations. Let's put this as number 2, equation 2. Also, keep in mind that GME, this is a constant also, this is the relationship. GME, the gravitational constant times the mass of the earth, is the same as the gravitational acceleration times the radius of the earth squared. Keep this in mind, equation 3, because we are going to use it. So this is the relationship between them primarily. Now, what is now the acceleration of bodies that are not within the earth? Acceleration of bodies that are not within the earth, okay? I wanted to say acceleration of bodies based on planets, okay? Now, you know what, one of the things that we're going to use this thing to do is to, this value here, if you plug in the value of the mass of the earth, and you plug in the value of the gravitational constant, and you plug in the value of the radius of the earth, you are going to get this value, okay? But actually, one thing I want to do is, let's try and get the mass of the earth. I think the mass of the earth can be gotten this way. So the mass of the earth, before we move to that thing I said, there is something I want us, so that you see the use of this thing. So the mass of the earth, therefore, can be equal to, from here, G R E squared over G. So by the time you solve it, it becomes m sub equal to, remember that the value of G is 9.81 meters per second squared. R sub E is a constant. It is 6,400. I can't remember. I think it's 6,400 kilometers, right? That is 6.4 times 10 to the power 6 meters. 6.4 times 10 to the power 6 meters. So that's 6,400 kilometers. I'm correct. Okay. So then the G has been given already to the 6.67 times 10 to the power. So I want to write all these constants down first, because that's what I did before you solve, before you do this thing, before you deal with this celestial mechanics, you have to know some constants, okay? So those are the constants I first wrote down. And so it's power minus 11. By the time you work this, you get that m sub b equal to 9.81 times this squared, right? This guy is squared. That is 6.4 times 10 to the power 6 meters all squared over 6.67 times 10 to the power minus 11. By the time you solve this, the mass of the earth will give you 6.4. Let's square that. 6.4 times 6.4 is equal to 40. Then that times 9.81 is equal to this divided by 6.67. Notice I'm only dealing with these numbers, right? So that gives us 0.24 times 10 raised to the power. Here, I've squared this guy, that's 12 minus 11. So mass of the earth becomes 60.2 or 6.02 times 10 raised to the power. Now here, I've included 1. So the 1 plus 12, that's 13. 13 plus 11. Okay? So that becomes 24. That's 6.02 times 10 to the power 24. And that will be the mass of the earth, kg. M sub b. Don't forget your distance. So that's the mass of the earth. So that's the constant. Now another thing is, oh Jesus. Okay, it's still over. All right. So that's that. Now another thing we could do is that we could try to calculate the density of the Earth. Okay. Now one of the ways we can calculate the density of the Earth is this. Density of the Earth. You see, we can use this formula, these things, to generate many things about the Earth, the properties of the Earth. We could record that density is equal to mass over volume. So we need the volume of the Earth, right? Mass of the Earth over the volume of the Earth. So first, let's remember the volume of the Earth is going to be the volume of a sphere. Since the shape of the Earth is a sphere, right? Volume of a sphere. So we will say it's roughly a sphere. Let's say it was a perfect sphere. Even though we know it's not a perfect sphere. So the volume of a sphere, what's the formula for that? That's 4/3 pi the radius of the sphere, that's in this case re cubed. Pi r, yes, that's the formula. So this becomes 4 times pi times the radius of the Earth, which is 6.4 times 10 to the power 6 all cubed all over 3. So by the time we do this, we are going to get 4 times pi times 6.4 times 6.4 times 6.4. Then divided by 3 is equal to 1098.066 times 10 to the power. This is 18, okay? So let's call this the volume of the Earth, centimeters cube, okay? So by the time we use this to divide that, the density of the Earth will be what? 6.02 times 10 to the power 24 divided by, let's convert this one, it becomes 1, 2, 3. That will become 21 here. That will be 1.09. So that will be like 2. So let's just leave it at 1. Do you understand? If you 1.1 times 10 to the power 21 meters cubed. So 1.1 times 10 to the power 21. So that becomes 6.02 divided by 1.1 is equal to 5.47 times 10 to the power 24 minus 21, that's 3. So this is approximately the mass of the density of the Earth. That is 547,000 kilograms per meter cube. That's the approximate density of the Earth. Let's see that well. 1, 2, 3. Okay, 21, 3. Sorry. Times 10 to the power. Because the density of the Earth towards the center is said to be approximately like 10,000 kilograms per meter cube. So it cannot be this. This will be 1, 2, 3. So that will be 5,470 kilograms per meter cube. So that's 5,000 that. So it becomes denser the closer you are to the center of the Earth. So that's that. Now let's quickly talk about the gravitation of the value of gravitation or gravitational acceleration, okay, on different planets. So acceleration due to gravity on different planets. Now, here's what you come to find out. You recall that if I throw an object up, if an object is thrown up, v squared will be equal to u squared minus 2gh, okay? So if the object is coming down still, if the object gets to the top, I said if the object gets to the top, the v will be equal to what? 0, right? So that u squared therefore will be equal to 2gh. Now, if in a particular planet, if on Earth, this is the case, and in another planet, let's say in another planet, I throw the same object at the same speed, okay? So if I throw object up at the same speed in different planets, then this guy will be a constant. U squared will be constant across all the planets, which also means that this relationship GH will be what? Constant across all the planets, which means that the relationship between G and GH will also be what? Constant across all planets. What that means is that according to this relationship, that G will be inversely proportional to H. So meaning that the height that the body will get to will be inversely proportional to the acceleration to the gravity. And that makes sense, right? The higher the acceleration to the gravity, the lower the height that it will get to. Because acceleration to gravity will reduce how much, how far it will travel. Do you understand? So my point is now that this guy, I wanted to say, yes, so this guy will now be G1. So if GH is constant, then G1H1 will be equal to G2H2. So for planet 1, so this will be gravitational acceleration of planet 1, height in planet 1, gravitational acceleration and height traveled in planet 2. Is that okay now? So you can also say that G1 over G2 is equal to H2 over H1. So you can also use this equation. There's a case where you use this equation, you'll be told that if the acceleration, if a body travels a height 1.5 meters, for example, or 3.5 meters in a particular planet that has a gravitational acceleration of so and so, what will be the height if it is thrown at the same speed in another planet that has another gravitational acceleration? So this is the relationship between them. Is that clear? So that said, let us now go into, let us talk about the gravitational weight of different objects, on different planets. No, not even on different planets. Let's first talk about the gravitational force depending on the position of the object. Okay, the gravitational force depending on the position of the object. The gravitational force will actually change depending on the position. Gravitational force will change depending on the position. Let's take three positions. The first position will be this, where the object is exactly on the surface of the Earth. So the force of gravity will be equal to G ME times the mass of the body. Let's say this body has mass M over R squared, with R being the exact radius of the Earth. Because from here to here will be the radius of the Earth. So the body is lying on the surface of the Earth, then this will be the case. Is this clear? Then also, what will be the force of gravity for, so this is case 1, okay? This is case 1. So how about case 2? Where the body is actually some distance away from the Earth. So if this mass is some distance away from the Earth, by the time you estimate this will be R plus, because from here to here is R, then plus a particular distance from here to here. Let's call that H. So that distance will actually have effect on the force. So that will be GME times this mass all over. The distance will now be R plus H all squared. Is that clear? Then for case 3, where the object is inside, somewhere inside the Earth, like this. So, and from this distance, R will be, there is a distance away from the surface. So some H distance away from the surface, right? So this becomes F will be our F. I'm trying to rush because of the space on my phone, but just try and understand. See, you mean to get all these formulas and how they are derived. You can by yourself use them when you see questions. So the force, just be listening to me. The force will be the gravitational constant times the mass of the Earth times the mass of the object over R minus H. Because there is now the distance between them now is not equal to the radius of the Earth again, and squared. So these are the formulas you will use depending on what you are given. Let me quickly clean the entire board first so that there will be enough space. So these are the formulas that you will need to calculate the force of attraction depending on the position of the body on Earth, or the weight of the body depending on the position. Now let's move to Kepler's law. Let's move to Kepler's laws. Okay, so there are 3 Kepler's laws, and the first one is that the first one is that the planets the planet's ellipse about the sun. Let me write it. The planets, or each planet ellipses so there's ellipse about the sun, at one focus. That is, what that means is that they go around the sun, with the sun being in a stationary position. Do you understand this? They go around the sun. And the second one is saying that the line joining the planets and the sun, sweeps out equal areas in equal time interval. Now the third one is that the period, I'm going to derive the equation for this one. The period, to prove it, okay? The period T of revolution of each planet, is proportional it's supposed to be the square of the period is directly proportional to the cube of the radius between them, of the radius of the planet, and the distance between them rather. So the square of the period, number 3, the square of the period. How do I know? I'm going to show you in mathematics, okay? The square of the period, T, of revolution of each planet is proportional to the distance, the cubic distance, the cube of distance between them. Let me open the door. Distance between them, between the sun and the planet. Okay? Now let me quickly show you something. You know that there's going to be a force of attraction. Between the planet and the sun, right? So, and these planets are moving around the sun. So the force of attraction is going to be equal to the centripetal force of the body that is moving in a circular path, right? Since we assume that it's a circular path because we say that the line joining them sweeps out equal area in equal time. So we know that it's a circular path. So the force of attraction, Newton's gravitational force, will be equal to the centripetal force. So we have that Gm, mass of the Earth, times mass of the planet, over r squared will be equal to m. What is centripetal force? mv squared over r. Does that make sense now? Now, recall also that this centripetal force, mv squared over r is also equal to mr omega squared, because v is r omega, right? So if v is r omega, then r will cancel r, that kind of thing. Is that clear? So, and this r is big R now, in this our case, right? So it means that our formula can therefore become Gme, let me just use small m for the planet, over, ms, is the mass of the sun, this is the mass of the planet. So mass of the planet. So ms, not me, please. Mass of the planet, mass of the sun, mass of the planet, over r squared is equal to mr omega squared. Now, if I bring r here, it becomes Gm sub s m is equal to m omega squared. If I bring r here, it becomes r cubed. Is that right? So recall again that omega is equal to Remember that omega from centripetal motion, right? Circular motion. I will link it in the description so you see. It's actually 2 pi over t. That is 2 pi f, that which is 2 pi over t. By the time I bring that in here, it becomes g mass of sun times mass of planet over r cube is equal to m 2 pi t, that is this all squared. Is that right? So mass of planet can cancel mass of planet already. So from there, I can therefore have that Gm mass of sun will be equal to over r cube, of course, will be equal to the square of this 4 pi squared over t squared. So from what I have here, you can already see that t squared Gm, so that is equal to 4 pi squared r cube. Now notice that the mass of the sun is constant, gravitational acceleration is a constant, this guy is a constant. Let me just write it this way. T squared will be equal to 4 pi squared r cubed over Gm sub s. So these are constants, right? So 4 pi squared over Gm sub s are constants. So t squared will be equal to kr cubed. This is that, so they are directly proportional. So this proves it. Is that clear? Now, let me quickly roll you to this guy. There are many things you can also do with this Kepler's law, but we're not doing now. So let's quickly talk about Earth satellite. Okay, so the Earth satellite. So any object that is moving around the Earth, okay, could be termed as a satellite. And there will be 2 of those types. There will be a natural satellite, such as the moon. There are natural satellites, such as the moon, okay, and there are artificial satellites, such as the one we use for communication satellite, the one we use for communication, for communication, and which other satellite do we have? Which other satellites? Okay, basically communication satellites, okay, those ones are artificial satellites. Nigeria launched its first satellite, I can't remember. Okay, but let's just quickly see through this. Now, there's something that you should know about satellites. Now, satellites are actually falling continuously towards the Earth. Okay, so but why do they never cease? See, this is the Earth. Okay, the satellite is constantly going around the Earth. It's always going around the Earth. Okay, it's always going around the Earth. Why is it able to go around the Earth? It's actually because in this surrounding here is the satellite is moving around a constant path, and that path will be called its orbit. Okay, that path that the satellite takes is called its orbit. So now, why does it continually take that orbit? It is because it's constantly is actually being pulled towards the Earth by the gravitational acceleration, the gravitational force. But why is it not always entering the Earth? The reason why it's not entering the Earth is because of this thing. When it is being pulled towards the Earth, the body is accelerating. The velocity of that guy is tangential to its path. So it is always horizontal. The velocity is always horizontal at any particular point. So if it's moving around the Earth like this, the velocity is always horizontal. So it is always being pulled towards the Earth, but it is not entering the Earth because it's moving at a particular speed that is enabling it to just to not fall into the Earth, but to just pass around it, to move in a curvilinear path, so that the Earth is always as if the Earth is curving under its path. Is that okay? So that is what the Earth's satellite is about. Now there is a way that is also derived, since the satellite is always drawn towards it. Let m sub s be the mass of the satellite, so that the mass of the force of the satellite is its weight, right? It will feel its own weight, and it will be equal to since it's moving around, it's going to have centripetal force, right? So m sub s g will be equal to mv squared over r, which is with r being the distance this is the mass of the Earth. No, the mass of the guy. Okay? So So this r is the distance from the Earth, okay? The distance of that satellite from the Earth. But of course, we already know that since there is also gravitational force pulling it, then either of these can be equated to, so I'm going to equate this one, m sub s v squared over r, to the gravitational force that is fused, mass of the Earth times mass of the satellite over r squared, which is the distance between them. So m again cancel m sub s. Is that clear? Now, here's the deal. This radius is going to also cancel one of the radius here, right? So v squared will be equal to gm sub e over r. Now, remember that gm sub e, we did something here just now, that gm sub e, recall that I said that gr squared is actually gm sub e. Do you remember this? We generated this formula before. So if that's the case, gm sub e, I can use this substitute it so that it becomes v squared, the velocity of that satellite that is enabling it to be able to maintain that orbit around the Earth is going to be equal to gr squared over this r. Is that okay? Now, this will take care of one of this because it will be the same radius. So v squared will equal to gr. So v will be equal to the square root of this, so that the velocity of the satellite is equal to the square root of gr, which is the radius of the Earth. Is that okay? So this is how to calculate the radius of the Earth. Actually, if you plug in your values here, you are going to get a value that is equal to the velocity at which this thing is traveling. A satellite that is moving around the Earth and will not fall into the Earth like that is traveling will be around, what is that value again? That is going to be 8 kilometers. That's about 8 kilometers per second, 8 kilometers per second. By the time you plug in your value, you can try it. You're going to get about 8 kilometers per second. Now, there is one other thing you have to learn, which is called the parking velocity. Parking orbit, I said parking velocity. That's 2.9d. Huh? What can I do now? Let's try to finish it. Let's quickly learn on what is called parking velocity, parking orbit, not parking velocity, please. Now, what is parking orbit? Just stick with me, you're going to understand it. What is parking orbit? Now, the other name in my here is geostationary orbit. Geostationary orbit. Geostationary orbit. Now, why is it called geostationary? The word stationary means that it is as if it's staying, right? Now, if you have ever observed a satellite before, and it's as if the satellite is standing still, it is because of this. The satellite is moving at a particular, the satellite is moving at the same speed of rotation of the Earth. Is that okay? It is moving at the same speed of rotation of the Earth, so it will have the same period around the Earth. So since it's having the same period as the Earth, the period of the Earth around the Sun is 365 days. So the period of rotation, not revolution, sorry, the period of rotation of the Earth is 24 hours. So that same guy, that satellite is also having the same period of rotation around the Earth. So if you're observing it, you are going to be seeing the satellite in the same place because it's having the same period as the Earth. Is that okay? Now, one of the things we can use to do that is to derive an expression. Can we derive an expression for that? Actually, we can come here to, since the body is moving around the Earth, why am I forgetting things now? Since the body is moving around the Earth, okay, it's moving around the Earth at the same period of the Earth. Recall first that the velocity of the Earth is equal to the circumference over period. Okay, you remember this law? Just look at my video on circular motion. I explained why this is the case. Circumference over period, right? So the velocity of the Earth is going to, or the velocity of that body is going to be 2 pi the radius of the Earth over t. Do you understand? So over t. So one of the things that we can find is what distance away from that Earth, away from the Earth, should that satellite be placed such that it can move at this period exactly. So that's what we want to find out. What distance away from the Earth would this guy be placed? Now we can bring in our equation again that the gravitational force will be Gm, mass of the satellite, times mass of the Earth first, times mass of the satellite, over r squared, which is the distance that must be between them. Now this distance should be the distance, the distance that must be between them is equal to mv squared. We just put this somewhere, okay? Let's call this equation, we'll not be naming our equation, so name it please. Mv squared over r, which is still distance between them, okay? So if the guy is moving around it, I'm trying to make sense of this. And this mass is the mass of the satellite. This will take care of this. So we have Gm sub b over r squared is equal to this squared now is going to be this guy all squared, right? That will be 2 pi r all squared over t, then r. T is also going to be squared. Okay? So by the time you work this out, t squared r will be equal to, by the time you bring this guy here, you cross multiply, you interchange. Okay, let's cross multiply. It becomes t squared r times gm sub b equal to r squared, 2 squared, 4. So 2 squared is 4, pi squared, r squared, then dot r squared again. So that will be r is power 4, right? So r can take care of 1 r, so it becomes r cubed here. So t squared here will be equal to 4 pi squared re cube, okay, is re, radius of the earth, over gma. By the time you plug in the value of this, the constants, because these are all constants, right? These are all constants. By the time you plug in the value, you get the actual period of the earth. Then you take the square root. You will be able to get the actual period at which that thing must be rotating. Okay? The period of the earth. You are going to get that. But that's not only what I want to get. Okay, this is what I will do. If you want me to explain Earth satellite more, I'm going to, let me know in the comment section. I'm going to make another video on that. Then also solve questions. But in the meantime, there's something I must deal with if this video must be complete, okay? So that is for gravitational potential. Now, gravitational potential is just, the gravitational potential is just like potential, just like electric potential. It's going to be the force per unit mass. Okay, so that is the gravitational potential at a point is the work done in bringing a unit mass from infinity to a point. Is that okay? From infinity to a point. So that now it's called G. Okay, it's called G. But if we wanted to work it out, we will say that this is what gravitational potential is. Acceleration due to gravity is actually gravitational potential. But what of gravitational potential energy? Gravitational potential energy. Now we said it's the work done, right? It's going to be work done, right? That will be work done in bringing a unit positive charge. Okay, in bringing a unit point, a unit mass. So the work done will be equal to 4 times distance, as you already know. So if the distance is a small distance, dx, let's call it dx, then the work done will be equal to, let's call the work done the energy U. Let's call it U. Okay? So that it will not be the same as V that we're using in the other guy. So let's call it U. That's potential though. So that will be force times D times dx. Now what is force? Now to get the work done, the gravitational potential energy from infinity to a point is going to be the, by the way, how am I rushing? G will be equal to force, which is Gm over m. So this takes care of this over r squared. Remember force is Gm over r squared. So the value of G can also be Gm over r squared. You see, it proves what we got the other time. Okay, so this guy. Now this force will now be, so to get the work done, we integrate it over the distance from infinity to a particular distance r. Is that okay? So if we integrate this guy, we'll get work done, we'll get U will be equal to F which is GMEM over r squared. In this case, it will be x squared because that will be our distance, dx. Is that clear? So by the time you integrate this guy, this constant will move here, so that becomes u. Integral of this will still be u. Then integral of this guy will give us GMEM will move out, integral of 1 over x squared. So you are integrating 1 over x squared between infinity and r. So by the time you integrate this, you are going to get 1 over r, 1 over x. So if we substitute, it becomes, since it's a definite integral, so it becomes GMEM times 1 for r, that becomes 1 over r, minus that of infinity, that becomes 1 over infinity. And 1 over infinity is 0, so that we'll have G gravitational potential energy will go to GMEM over r. So this is the formula. So don't forget, okay? Don't forget. What else? So escape velocity. So the escape velocity for a given body is going to be, for a body that is going to move out of the Earth, the body is going to have a particular kinetic energy, right? It's going to gain a particular kinetic energy, and it's going to have a gravitational potential energy at any point on the Earth, right? At a particular point on the Earth. So we equate the kinetic energy. So for escape velocity, obviously I'm not cut. See, the reason I'm rushing is because the space on my phone is not much, okay? And I don't want it to cut. I want to finish this. Very 1 gig I remember. So we are ending it at escape velocity. The escape velocity, I've already done this in 30 days of physics and 5 days physics. So do well to see that video also. So escape velocity will be equal to the kinetic energy that the body has, and it will be equal to the gravitational potential energy at any point. Okay? So that will be half mv squared for the body will be equal to gravitational potential energy of the body is GMEM, mass of the body, over r. So mass of the body cancels mass of the body, so that we have v squared will be equal to 2GME over r. Is that clear? This r will be the big R, right? The radius of the Earth. So by the time we have v squared, so v will be equal to the square root of 2GME over r, or now you remember again that GME is what? GME. We did GME, G sub n, GM sub v equal to GRE squared. You remember that? So I can bring that in here, that v will be equal to the square root of 2GRE squared over r, right? So this takes care of this, and v will be equal to the square root of 2GR. Okay, by the time you calculate it, if you slot in the value of g, so in the value of r, you get 11 kilometers, 11, escape velocity will be 11 kilometers per second. Alright, so this is what you do. You plug in the value of r and you get the answer to the escape velocity. If you need me to give you questions, reach me out on that number. Also for this textbook, don't forget. Alright, so that's if you have problem with, especially the things I did here that you might not understand. So God bless you. Thank you.